Hello everyone. We are going to do some differential data flow computation today. Particularly, we're going to try to write up 6 relatively simple computations, graph computations, in differential data flow. So I was asked to do this by a master's student at Edinburgh. And although I was asked to do it for timely data flow, because timely data flow goes fast, I thought I would do it for differential data flow, because differential data flow is a little easier to write, and I don't know, I kind of think it has more interesting trade-offs. Timely data flow is a bit like writing some raw code, and yeah, you can make that go fast because you can just write whatever you want. So we're going to try to actually use the idioms presented in differential data flow to implement these 6 tasks. You can see them here. PageRank, triangle counting, single source shortest path, connected components, undirected connected components, the nth degree neighborhood. So this is for a given n, the set of nodes within n hops of a specified vertex. In this case, it looks like n gets to be a part of the program. And vertex reachability, which is whether a target vertex is reachable from a source vertex, just a Boolean. I might be misunderstanding some of these. So, like for example, it looks like vertex reachability is pretty simple if you've done single source shortest paths, which tells you from a source vertex to destination its length. We will see. So several of these, fortunately, are already written in various examples in differential data flow, but I thought I would collect them together in one project, so rewrite them as I go, so that rather than being sort of straggled across a few different repositories and directories, we actually have them in a place that Blavlos, for example, can go and investigate. So let's do that. I'm going to go and make this a bit bigger, switch over to a work in progress directory that I have. We will look here and see what's going on. Let's do cargo new graphs. Now we've got a graphs package, and we're going to dive into there and think about making 6 binaries. I'm going to try to make one binary for each of these projects, and possibly, possibly make a little bit of a library thing. I guess I'll have to switch this from to source/lib. A little bit of library code that will help us do things like, for example, load graphs for us. So let's get started. I guess we're going to start with the library code, just because we kind of need that before we can do anything else. So we're going to go and open, we're already here. This just happens to be the name of the previous project I was using, and so fortunately we're just right in here. There is no fun main. Let's edit up cargo.toml. We've got some dependencies, and I've just pushed recent versions of timely and differential data flow to crates. We might use those. We might also, well, let's just use those. We'll use a sketchy version of triangle counting that doesn't use the awesomest tech, unless we decide to change that later on. So we can just do timely equals 0.10, because that's the version on crates. Differential data flow, goodness. Differential data flow gets also 0.10, that's what's currently out there. Save these folks, and there's nothing here yet, but I forget if we can we take an empty lib and build it? Let's see. What do we need to do that? Still learning to pilot this new keyboard, and also to pilot VS Code, and just a few other random little bits and things. So occasionally there might be some sputtering and stuttering, and possibly some cursing on my part. That's too bad. Might as well start typing some random things here. So we're going to have some types. Let's, for example, have a node type which we'll set to be something simple at first, like U32. I suppose we'll want it to be a public type. We'll have, these are not actually interesting types, they're just aliases, but it helps, for me at least, when I write code, to remember the intent of what I'm writing. So, edge, for example, we prepare 2 nodes. This is going to be a directed edge. Awesome. We're going to have pub type time. So when our data change, nothing that I was asked to do involved changing of data. We're going to write the code that way anyhow. And if we want, actually, let's just do batch computation for now. Here, time is the empty tuple, and that's great. This is, you might be surprised to learn, a valid timestamp in timely data flow, and all that it means is that there's only one time, and when that time is done, we're all done. It's basically like a batch computation. It's sort of like you have the value 0 for your timestamps and no other values. Here we just have the empty tuple value. We're going to have what? We've got some other things that we could in principle do. I might as well just write things for them. Iter. So if we need to do any iterative computation, let's try out U32. So by default, differential data flow is going to pick usize for us. So this will only actually come up if we get into writing our own custom loops. We probably won't do that, but I'm just going to drop this here so you can see it. And we'll also do a diff type, which let's just make the isize for the moment. These things aren't strictly necessary at all, but it's often the case that when you're writing programs like this, you want to potentially play around with the sizes of some of the data types that you're using to see if that has an impact on performance. So we might want to use up to 4 billion node identifiers. We might want to use 64-bit identifiers as quite larger. We could, in principle, even use strings or something like that for our nodes. We'll probably actually try to see if we can write generic code that accepts arbitrary types of nodes. Because we can. In fact, let's just do that now. So edge is now generic with respect to some type n, and it's just a pair of whatever those are. So we can have an edge of nodes. That makes sense. And as we change the node type around, or if we have one generic parameter, which is the node type, we can drive various edges around. Okay, that's great. We're going to want, for sure, a function to load up some data. Load graph, let's call it. We're going to give it a file name. Which is going to be a string ref, and it's going to produce what? Probably, let's just do something utterly primitive and do vec of edge of, geez. I have some clever, super generic ideas in place here, but let's just do node. And we could have tried to make this generic with respect to any type that implements from of stir or try from maybe of stir, but basically let's not get super complicated just yet. So how do we want to do this? There's a file format that I use that I have a fair bit of data written down in, and I was going to try to use that just because it reads really quickly, and so we're not going to have to spend necessarily a lot of time watching data get read from disk. So let's do that. This is a library called graph map. And I have no clue what version it is. We're going to have to go find it out. Let's actually just quit my mail program here. And where are we? Safari. We're going to go to crates. We're going to look for graph. It is, right, it is basically nothing in particular, 0.1.0. Some quotes around that. And all that this really is a handy little library for taking data initially in text format, like pairs of integers in text format, turning it into a nice flat binary representation and letting you read that back in as fast as your computer can manage, which is handy. So we're going to we have one of those things lying around. I'm going to see if I can remember how to read this stuff just by copying and pasting, because that's the way real people do computer science. So over in the graph map thing, we have, for example, a print, which shows us how to load up one of these things, and I'm just going to steal it. And oops. So file name, okay, we're not going to take the file name that way, that's ridiculous. Delete that. We've got a new, what do we need to do? Graph map. I think 2018 doesn't require us to do these external create things, but let's see if I'm totally wrong about that. So what it allows us to do is spin through all of our graph nodes here and essentially look at, I mean, the file is just there. Look at all the stuff. In the file, we don't need the degrees anymore. And what we might want to do is make this nice and data parallel and have an index, which is a usize, and peers, which is also a usize. And so this makes it easier for timely data flow workers to call these methods and indicate what fraction of the graph they'd like to work on, because you know, we don't need every graph, every worker to load the entire graph. So we can write, for example, if node mod. Node is the okay. So the nodes go from 0 up through graph nodes. It's just how things are. And if when we take that mod peers, we get back index. And this is a totally legit way to distribute the nodes in the graph across our workers. And we're just going to restrict our attention, if we are a worker with a particular index, to this set of graph nodes. What do we do? We're not going to print things. That's silly. We are going to instead start to stash them in our results. So let's let mute results be a new vector. So vec new. We can totally, well, we don't have to change lots of things here. So let's get rid of this line. We don't need that. We need to do something else instead, which is going to be to take our edges and stash them with our node in the vector results. We'll do results.push of node as node, comma, edge as node. And it turns out that the types here, node is a usize, so that this node goes up to usize, and each of the edges is a u32. That might have been a bad choice on my part, but there we have it. So we could, in principle, actually make this is dumb, but you know, we make this generic and have it be anything that implements both from usize and from u32. But let's not bother to do that. And all that we need to do at the end is return results. So this is now a thing that maybe this builds, maybe not. It's always good to check in with your cargo check periodically so that you understand whether you've written a massive pile of utterly worthless code. But in this case, we have not. Let's make this public. We don't really need to do that, but we plan to use this elsewhere, and we plan for this to be relevant and meaningful. Now, in principle, we could load up a graph and print some stuff about it, look at the edges. Awesome. What we're actually going to do is wander on over to, let's close these down, to some new files. So let's make a new file. Let's save this as, here in source, we're going to create a new folder, bin, which is where Rust binaries go in a project. And what do we want to start with? What's easy? Let's go look at our requirements again. Oh, I quit the mail program, didn't I? Go moron. Mostly I quit it because it pops open periodically every time it disconnects and reconnects, and you can't get it to stop. But let's see. We got PageRank. PageRank's actually one of the harder ones. Let's do well. Let's just make files for each of them. So we've got PageRank.rs. Awesome. 2, 3, 4, 5, 6. We'll see how many of these we can actually remember because we're smart. We've got great memories. Triangles.rs. Awesome. We have connected.rs for connected components. We have sssp.rs for a single source service path. We have reachability, or let's do reachable.rs. And we have the neighborhood, nth degree neighborhood task. So let's do neighborhood.rs. Sweet. Okay, so we now have several tasks in front of us, and we need to think about writing some programs now. And what's a nice? I'm trying to think of a nice, easy one to do. The neighborhood one actually might be the easiest. Several of these. So just give you a rundown. For example, PageRank is written. Actually, this is going to be. We're going to steal it from the differential repository where it exists, and I'll talk you through it. But we're not going to spend a lot of time. Hopefully, not a lot of time finding bugs and worrying about stuff like that. We have several examples of triangle computations already, mostly in the dogs subproject. We can steal one of them that does not involve that subproject. It's not published on crates or anything like that. We could bring it in principle, but it's just in a repository somewhere and on my local laptop. Connecting components, super easy. Like, we've written this a lot. There's actually a method in differential dataflow has a, if you've not seen this before, has a graph, it has an algorithms subdirectory, and it's got some graph stuff in there. Graphs, awesome. And it's got a few different algorithms that are kind of cool and interesting, and we're going to steal some of. In particular, it's got propagate, what's that? And this is basically labeled propagation. And we're going to use that for our connected components algorithm. It's also got Dijkstra, which is bidirectional Dijkstra. We're going to use that for our single source service path and our graph reachability computations. Ideally, I've written it in such a way in the algorithms space that we can actually just use the code there in principle without having to copy and paste in the 80 lines of code that is bidirectional Dijkstra. If you're interested in learning about bidirectional Dijkstra, there was a blog post recently that talked about it in the context of the LDBC BI query 25 problem, which has us finding short paths between target vertices and then doing really exotic things like reconstructing the paths and scoring all the edges and then doing a bunch of weird-ass stuff that we wrote from scratch. It's not recorded as a video, but it is actually in this work-in-progress repo. You can just back down a level in the repository and you'll see it. You can also read about it in the blog post. I may try to talk through it because it's sort of cute. It's different. It's a great example of a thing that differential data flow is pretty good at that some other graph processing systems, and especially Datalog, are not good at, which is going fast. Maybe I'll say that because I like that story. But let's do instead the neighborhood stuff. So this is a relatively simple problem, right? We have a graph, and we have, in principle, we have a node or multiple nodes that are supplied to us possibly interactively. I don't actually know. And what we want to find is the nth, the sets of nodes in the n degree neighborhood. So if you're allowed to traverse up to, hopefully up to, n edges, not exactly n, that'd be awkward, but we'll see. Up to n edges, then there's some set of nodes you can reach, and we're going to return that set for each query node. So let's just start. Fun main. I don't usually write fun main because usually Rust has written it for me, but we're going to do stuff like that here. We are going to probably just dive right into a little bit of timely data flow. Execute from args. Executing from args is what lets us pass some command line parameters into timely data flow. Stood end of args. which lets us set, for example, the number of workers we want to use. Do we want to do things distributed across multiple computers? Lots of stuff that we're not really going to be doing very much here, but it's, a fine way to think about it. And now we, like pretty much all timely data flow programs, we now write what is essentially a closure describing what each of the worker threads should do. And the intent here is that this is hopefully idiomatically like what you would do if you're writing a single-threaded execution, and you're just going to happen to use operators, these data parallel operators, that cleanly run when we run multiple concurrent threads, and you shouldn't have to think about all the different workers. Now, that's not exactly true, because we're going to have to think about the fact that we have different workers when we load up the graph, for example, but we try to keep that as simple as possible. So let's grab file name. We need to open up our file, right? So file name is going to be std env args.env1. Oops, one. We really hope it's there, but we should complain if it is not. Must supply file name. This is way better than just crashing and not knowing why you crashed and having to go find the source code again to figure out what's going on. We're going to let index be worker.index. I'm not really sure we actually have to call this, but we don't necessarily have to bind it to a local variable, but let's do it anyhow just to remind everyone where these things come from. And now we're going to grab some edges. Let edges be, what was our method called? So it's back in, I think we need to use it in the graph namespace. Load graph of file name, comma, index, comma, pierce. Neat. Let's actually let's take a moment and see if this is roughly working. We're going to print out the number of edges we loaded. Loaded some edges, boom, edges, len. All right, does this build? Neighborhood. Nope, does not. Oh, so env, not env. Yeah. And this thing is, I guess we're supposed to have a semicolon at the end. Actually, what we should really have at the end of our timely data flow computations is a dot expect timely computation failed to start. So what we actually get back when we call execute from args is a result containing a bunch of handles to the various worker threads. And if the result comes back as an error instead, that means that somehow we didn't manage to actually get going, and we should clearly indicate that as a responsible computer program. All right. This is supposed to be not a string, but a string reference. We can fix that really easily. Ta-da! Great. All right. Let's see what happens if we run it. Let's not. This should build pretty fast. So, and let's give it live journal, maybe. Live journal is not so big. It's about 4 million nodes, maybe, and what I want to say, like 68 million edges or something like that. In which case, this takes, I think, once it gets running, maybe 20 seconds or something like that. No, maybe, sorry, 20 seconds is like to parse it. I don't remember. We'll have to find out. The actual loading the graph is super fast. It's just memory mapped file. And then, actually, yeah, no, that should be super fast. We're just going to grind through 68 million entries and push them into a vector, and it's all good. If we were really clever, we could probably anticipate roughly how many edges we would need by looking at the number of edges in the graph map, but I think it doesn't even expose that because I didn't think that far ahead. That would save us. Sorry, more conversation while things build. Yeah, that would save us from doing multiple reallocations as we push edges into that result while we're loading the graph. So that program load graph, that function is basically just going to be doing, because it's not mem copying, but it's just going to be blotting some memory around. It's not doing any interesting compute or any interesting I/O or anything really interesting at all, to be honest. It would be amazing if there was a cache of all of these things somewhere. I'm going to have to look into that. In principle, one of these things is this CC cache or something like that will keep these build artifacts around, but let's at least just hope we don't have to do this for every binary that we're building. All right. Yeah, cool. That's not very many edges. Why is it so small? I think it should be, I feel like it should be 68 mumble. Let's see, I have a few. This might have been messed with and deoriented, basically. And we'll just work with it anyhow. So there's oh no, we're gonna need to fix this, won't we? It's just it happens to be these algorithms are direction dependent, and if we've undirected all the edges, then it's gonna be really boring to like only walk in one direction on them. Let's see if I have another copy of this around somewhere, or let's see actually what's in. Says it. I don't really want to use Twitter because that's enormous. But I do have sock livejournal 1.txt, and we can totally just in our spare time wander on over. Let's get a new terminal. Wander over to GraphMap land and have it parse this for us. I guess you get to see the wonders that are so what are these silly projects called? Graph-map, all right. So there's a parsing thingy that will happily munch on text data. For example, if we look at that sock livejournal stuff, that is a bunch of edges that look like so, and we don't want to do anything else here. And let's see if we run, let's see if I've been smart and I have actually put the arguments for no, I didn't. Well, sorry, I did put them there, but it panicked also. So source target strings is optional. This is if we want to treat our initial data as string data as opposed to integers, but we know it's integers and we just want to use those. We want to sort the data. We could dedupe in principle. What does reorder do? I don't remember what reorder does. Undirect, randomize, symmetrize. I think we just want to do sort and dedupe. The intent is that you can make an arbitrary pipeline essentially of these actions. So if you wanted to, shake your graph around, it would randomly, and then symmetrize it, and then reordering, if I remember correctly, changes the integers assigned to each node, but keeps the same topology. Changes the order so that degrees are more balanced, but we're not gonna do that here. So we're gonna our source is that livejournal thing, data sets, sock livejournal, and we want to produce something. Let's drop it into data sets again. Actually, to be honest, I would rather have the unadjusted data as my livejournal data, but I don't actually want to overwrite raw, let's say, raw space, sort dedupe. Sweet. It'll take a little bit of time. It's parsing text into integers takes surprisingly long time, which is one of the reasons I like leaving things as binary text. Actually, let's see how long it takes. We're going to leave this going, but if we just time this, then when we finally come back, we can see how long it took. All right, but we're going to just write some code now as if we had what we wanted. We've got some edges loaded up. Yeah, there's a few ways we could rig this, depending on how we want to time things. I don't actually know if data loading is meant to be part of the process, but let's just put in various helpful printouts about how long various things take. So once we've loaded up the graph, for example, we can print out what I like to do personally is drop a I guess it's so painful to write these things in this new keyboard layout because I did not put these keys close to each other. T. So now we just drop in timer.elapsed in front of everything. We basically get something that looks a little bit like a log report. And it tells us when things happen, so we can get a read on, like, holy wow, it took a really long time to load the graph, or something like that. So yeah, we're going to build a new data flow now. This is just going to be the data flow that does our degree n reachability computations. So I can think of two ways to do this, but let's just both of them start the following way. So we're going to build up a scope, and into the scope probably we want to just dump all of our edges. So edges might implement as collection. Let's see. Edges, certainly everything that is iterable has implements this extension trait called toStream. We can turn it into a timely data flow stream, and it's just all of that data at time 0. And that's basically what we do with our edges as well. But I'm not actually sure if we have such an implementation for differential data flow. That would make sense, though, wouldn't it? So often I deal with streaming setups anyhow that I don't worry too much about how to ergonomically dump a pile of static data in. This is where as collection lives. Looks like as collection is only, well, here at least, only implemented for streams. So we'll need to roll this ourselves, by which I mean turn this into a stream. It is when you turn something into a stream, we're going to need some extension, some imports to get access to these methods, but we need to tell it what scope we'd like to turn to a stream in. Once it's a stream, we want to change it, because right now it's just a bunch of edges. Timely data flow doesn't know anything about differential data flow's internal representation, so we're going to need to go and take every edge and turn that into a triple of edge, comma, time, which is going to be 0, comma, diff, which is going to be 1. Cool. And now we would call as collection, because this now has the right structure for differential data flow collection. So all that we've done, any timely data flow stream can get turned into a collection if it has the structure of a stream of triples, update triples of data, time, and diff. And the interpretation of the collection is the accumulation of any supplied changes integrated over time. So all that we're really saying here is at time 0, include all of these edges with a +1 number of times. So we'll just let this be our graph. And we're going to have another command line argument, actually. So let's add that in. N, which is the, it's not a great name, but that's the one that is used. The number of steps we'd like to go out, let's call it steps instead. Number of steps we want to go out from our source node. Possibly we want to actually let someone specify the source node too. That seems like that might be smart. Though also, actually let's, how are we going to do this? It'd be neat to just let people specify an arbitrary bunch of nodes and we'll do each of them in turn or something like that. But we have to have somewhere to break out our timely data flow arguments. You know, we don't just want to hand a whole bunch of 1, 2, 3, 4s and stuff like that into our worker. But let's just try it. Sorry, we're gonna do a simpler thing for the moment. I don't want to spend the whole day writing exotic. I do not want to. What did I press? Writing exotic argument parsing things. This is, for me at least, this is the hardest part. Okay, but these are not just strings. These are meant to be integers, so we need to supply steps. Parse. Let's parse it as a size. Do another expect here to say we're very unhappy with you. It's not actually parsable. Parse steps. And I totally should have copied and pasted all of this stuff as well because it's basically the same. Ta-da! Great. Okay, except I must apply source. Could not parse source. And this is actually going to be a node, which we'll probably have to pull in some using statement once we get around to people complaining at us. Actually, this will be later. All right, sorry. So we have now we have our graph. We don't. I think, well, what I would like to do is break this into two parts. Time associated with loading the graph, and then time associated with determining the neighborhood once supplied with the source. So let's load our graph here, just like we're doing. That's fine. This will take some amount of time. We won't worry about this too much. But let's also create a new input, handle and a source. So when we create new inputs in scopes, new collections actually, I should say, that's what we're going to do here, we get two things back. We get back the collection itself, that's the second argument, result, and we get back a handle, which is something that we can return to the outside world, which will let us interactively play with that source of data. It lets us move information from our host program here into the worker threads that are hard at work data flowing their little hearts out. So we're eventually going to return handle, but we'll have to do some more work inside, and we'll probably need to do a few more things as well, including setting up a probe so that we know when we're done. But if we have a source, and let's imagine that the source is just a collection of node identifiers, possibly empty initially, and then a single node identifier once we want to get going. What do we need to do? We need to take our collection of edges and repeatedly do some, I think, some semi-joining, basically. So informally, oh no, good. I've thought of a thing that we can have in addition to the node, which is going to be the number of steps that we have still to do. And that's exciting. So let's start by saying we're going to take source, which is just a, whoa, oh cool. We can actually, sorry, it just occurred to me that we don't have to commit to this in the program. We can specify this as data as well. So we can write a program that happily takes source inputs that are pairs of node identifier and number of steps to do, and fire that off at some iterative computation that will go and run and come back and tell us everyone reachable from that node in that many steps. So let's write that. What do we do about that? So source is now this pair of source and number of steps. We're going to have an iterate method that takes essentially like, there's a sort of remaining number of steps to take for each of these nodes. I don't know what I want to call this, inner, maybe? I don't have a better name off the top of my head. And what are we going to do? We're going to take this and take some steps along our graph and decrement the counter associated with the node. Actually, let's, as the very first thing that we do, or we could do this at the end. I was thinking as the very first thing we could do, we could filter down to the people who have at least one step remaining. So let's do inner dot filter, and the shape of this thing is a pair of node and steps remaining, and we want to do steps greater than 0, which should basically find people greater or equal to 1. People have 1 step left. Great. All right. We will then join this. Join this with our edges, and we're going to need to, unfortunately, we're going to need to bring in let edges be edges.enter inner.scope. Great. And now we can do inner.filter, join with edges, and maybe actually we'll do something smarter. We do a join map, which is a thing that lets us specify some logic as part of producing the output. So we've got a source, so a node, we have a steps, and we have a dest that we've reached. So we've taken 1 step along the graph, now 2 dest, and at this point, so here's a good question. Should we be maintaining, should we be able to do concurrent queries for different sources? And if so, we're going to want to keep track of, when we report that a dest is reachable, we want to keep track of from which node it is reachable. Now this is a massive waste of time if we only have to answer 1 question, because we wouldn't need to write down the node, but let's do that, just to see what a nice, robust implementation would look like. So what we're actually going to have then, instead of node comma steps as we go around, is going to be something that looks like, I'm just going to write this and then I'll explain. It's actually going to be a pair of current sort of location in the graph that we're talking about, and then the metadata about where did we start from and how many steps left do we have to go. So this is going to be not that, but it's just like a don't care, comma steps, and the root or something like that. And this is node. We care about neither what node are we at nor what root do we come from when we are thinking about throwing away all of these steps. And now what we want to do, I believe, is concatenate in a thing that we don't have in front of us at the moment. So we've taken 1 step, and what we'd really like to figure out how to do, oh wow, we can do this a few different ways, but what we'd really like to do is figure out a way to make this iterative computation end up with the correct answer. So the correct answer being everyone reachable in any number of steps. We've written something that will step forward a whole bunch of times and then throw all the data away, because if we keep stepping forward, we eventually get to 0, and then we throw the data away and we say, hooray, fixed point, the empty collection. So what we actually want to do is force ourselves to stay put on some of the data, and that's basically going to be our source data, actually. So let's modify the source data just a little bit. So whereas we started with, let's say, a node and steps, we're going to modify this to be that same node and steps. And all that this is saying is, in pursuit of nodes reachable from node, the first candidate is node itself. This is helpful because we can now bring this into scope also. Just source, I suppose. And we're doing this because this is actually what we want to concatenate in each iteration. So we want to what am I saying? We want to, as we take steps forward, we want to leave the option of any previously reached nodes as well, and we don't want to force them to vanish just because we step away from them and don't find another path back to them. So this will do this. This will keep us honest. And let's throw in a consolidate here too. We could do a few things at this point. We might want to actually, because what we're actually going to end up doing if we just do a consolidate, actually, maybe this is bad, is track all of the number of paths of each length to each of the nodes, and that's a count that could go up really high. Like that could, in principle, grow exponentially with every round. We could overflow some integers. So what we might want to do, this isn't even the best answer, but we might want to do is a distinct. The distinct will keep track of only the distinct destinations, nodes, and step counts that we've done. And we might want to go a step further, actually, and say, if we've already reached a node, it's not really that important to think about what we do the second time we reach it. So if we might do a reduction here where for each dest, node pair, we keep the maximum number of remaining steps. Let's not bother with that. That's fine. We just need to make sure in post-processing that we might see a destination multiple times. We should tidy that up in post. Either of those approaches is fine. I just want to try to keep it as simple as possible for the moment. All right. Yeah, look at this. This looks plausible to me. We're going to get out of source. Or neighbors be this. And perhaps we should do that thing where we throw away the steps and do a distinct. So let's actually add that in too. So what we got out of here was a bunch of dest, node, don't care. This is the number of steps that we took to get there, don't care. And we're just going to turn that into, totally screwed up the parenthesization here. We're going to turn that into node, dest. And then put a distinct at the end. And some of these are kind of optional. Like we could do things differently where we don't put a distinct. Distincts could do a bunch of work for us that is not deeply meaningful, but we're going to put it there so that we can have sort of tasteful outputs. And maybe let's add some code just to we can comment this in or out that is going to. I suppose we'll have to make an argument for it. Some inspect parameter that we will supply, but we could ask about the sizes of the neighborhoods, and maybe we want to see these things. So we could map our pairs of node, dest, node, don't care into node. We could then consolidate that and inspect it. And we can put our little timer thing, for example. Just take a few hours to type this out. Sorry. Put our little timer thing here, and we can say neighbors of blah is blah. Let's see if this works. Timer dot elapsed. Getting better with the keyboard, but it's not perfect yet. What are we looking for in here? We could just print out. Let's just do this instead. Sorry. we're just going to print out the record and it's going to show us various bits of logical time and stuff like that, rather than try to pick out the fields and what have you. Right, cool. Sources, let's add an inspect up here. We're going to parse it as a bool. Hopefully you gave us a bool. Now, this is a massive waste of real estate there. There we go. Now, what we can do, so we have this handle that we got back. We'd like to let the computation settle before we start interrogating it, or I think that's a good idea. So what we can do is, we're going to need to make this mutable. We return to handle grid. So if we do sources.advance to 1, these things start at time 0 initially, but we're going to advance it to 1 and then do sources.flush, which tells the system about everything that's going on, and then while what? Hold on. Okay. What we need to do at the moment is figure out a way to determine if we've seen everything that we need to see. And the way that we do this in timely data flow is with a thing called a probe. And a probe is just a little thing that lets us get information back out of a computation about how far we've, how far a particular point in the data flow has progressed through the times that are flowing through the data flow. And this is kind of easy to, we just get a timely data flow probe handle new. And to use it, we just throw in at the point that we're interested in instrumenting probe width, and it's a mutable reference to the probe handle. And now we're good to go. And now we can, outside of the data flow, interrogate the probe and ask things like, while probe.less than sources.time. So this is, as long as this point in the data flow has not yet caught up with sources.time, which we've advanced to 1. Data flow has the ability to catch up there once it's produced all of its work, but if that isn't happened yet, we're going to do a step, worker.step. And what this does is run the computation until timely data flow is able to confirm back up to us that all the changes have flowed through that bit of computation, that we're basically stable. We've seen everything that needs to be seen for time 0. And at this point, we can print that out. And we just need to do this and that, and this and that, to say that we have stabilized. Graph. Sorry, let's do this. Computation stable. Great. Timer.elapsed. Again. And we might then want to introduce the query node into sources. So sources.insert. What do we call it? A source? Called it source. Right. Source. That is wonderful, but nothing will actually happen until we do sources.advance to 2, and again do sources.flush, and then we're just going to steal all of this basically. Great. So this is the rough structure of the program that we need. We're going to start cargo checking it, and it'll almost certainly tell us that we need to bring a whole bunch of these methods into scope. But this is the intent, that we define our data flow graph with some hardwired graph edges in it, and we then, having defined the computation, advance our input 1 unit so that we can essentially run the computation with no query node in it, just to make sure that we don't that we cleanly separate the loading of graph data from the propagation of the query. We could also have put the query in at this point, but we wouldn't be able to disentangle the execution of the query from the loading of the data. Then we insert the source, advance the input, flush that information out, and do the same thing again to see when the computation has stopped. Now, I anticipate a whole bunch of complaining bits coming back. Yeah, great. So only 4 is surprising. Well, there'll be more, don't worry. So we, in line 27, there's probably some screwed up. Yeah, great. Semicolon that we didn't actually need to have. This type iter. So there's going to be a few types that aren't in scope. Let's bring them in scope. Actually, let's check and see that iter is. Let's not fight with things for the moment. I'll make this a usize. In principle, we can set this to whatever we want, but since it has to actually be the right, well, it doesn't really, does it? Let's change that back. Sorry, we're not actually using in the current computation. We're not actually using this as a timestamp. We're just using it to count down the number of steps remaining. So we can just have it be U32. We could have it be actually like a U8 if we wanted to. 256 neighborhood is probably pretty big, so we don't need to. But we're going to want also node probably. Iter. I guess we haven't used edge or anything like that. We haven't written this very generically yet. We'll probably try to fix that. Did we need anything else? Let's just see what the next component is. Node to stream method, that's true. We gotta copy paste this in. No method new collection. So that should be in use differential dataflow input. I believe. Or sorry. Input. New method named enter. Yeah, that's true. Hold on. Oh, we called it graph. I'm sorry. We called our collection here graph. Just called edges. Seems easy enough. And great. We're ready to look for a new round of errors. So no method named map. We need to have a use statement for map as well. It's a legit question. How many of these should just be on timely data flow streams or differential data flow collections as inherent methods? That's a fine question. Almost certainly, like if we ever reach a 1.0 with these things, there'll be some tasteful decision made there about how, come on, map and filter and stuff like that just needs to be there. Oh, right, we need to not just insert sources, but some number of steps. Oh, but we have steps. Good. So great. So I've got some more things to copy paste in. It had not occurred to me, as someone who largely maintains differential data flow computations rather than writes them from scratch, it had not occurred to me how frustrating, but how tedious these bits are. Usually I'm working off of some RS file that I've copied from a previous one and it's just included everything anyhow. Can't compare some stuff with 0. Okay, we'll need to put an ampersand in front of things in just a bit. Where was that? 45. Not 45 anymore, I guess. So yeah, steps is a reference to an integer here, so let's just make this be a reference to an integer also. And see what the word looks like now. We're going to need consolidate. What else do we need? Binary operation minus can't be applied. Oh yeah, okay. Well, hold on. What am I? Oh, right, okay. So our join is actually a little wonky here, sorry. So this node that we've got, when we've done our join between a currently reached graph node the route that we started from, sort of the source, and the number of steps. This is the intermediate or midpoint node that we're looking at the moment. This is not just steps anymore. This is source, comma, steps. And we don't want to record node there. We don't care at all about node. We want the source. We don't care where we just came from 1 step ago. We care about the root of our query. Now, we're getting closer. Timer does not live long enough. Fascinating. I think it's just complaining that we need to maybe do a move here. The timer is a type that can be copied, so we just need to warn Rust essentially that we're not trying to work with a reference to it, because that's crazy. All right, so this is dumb. because we had to move our timer in there, Rust is like, cool, I'll move everything in, including your probe, and we don't actually want it to move the probe in. We only want a reference to the probe. So what we can do, actually, let's not move the timer in there. We'll just oops. See, delete. I think this will work actually. If just in the context of this closure, we clone the timer. And this closure that we're writing, the worker.dataflow thing, it doesn't stick around or anything like that. We run it once, and so it's totally fine to borrow some things like probe, for example, and also timer. And now we have a local copy of the timer that can be passed into things like this inspect, which we almost certainly would have seen a complaint about in just a moment. Great. All right. Well, it looks like it's about ready to run, doesn't it? Let's see how our graph processing is going here. All right, so we did a bunch of data conversion. It only took 16 seconds. Okay, that wasn't so terrible. But we can go now and do a cargo build release of the neighborhood binary. Unused variable neighbors, is that right? Oh yeah, we don't actually do anything with it. And we've got an inspect on the end, but we don't return it for anyone to use. I'm not really sure if we're supposed to do anything other than, I don't know if we're printing the results, or if we're supposed to exfiltrate the results, or this part of the program requirements haven't actually been clearly spec'd out to me, but let's not worry about it for the moment. Now that we have a bunch of operators in here, it's going to take a bit longer to compile, but ideally we don't need to compile any more than this one time, because it's going to be super fast, and then we'll just call it a success and move on to the next thing. We might copy and paste basically the entire file, because almost all of this cruft is loading up our files, prepping a data flow, putting some data in, blah, 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 blah. How exhausting. So almost all of our programs have a very similar structure. And to be honest, I've only broken them into different binaries because I didn't want to have one binary with six computations in it, because the compile times on that would be unfortunately large. All right, let's try running it. What do we need to specify? We need to give it a path to our LiveJournal raw stuff. We have some more arguments. Number of steps, I think, right? Steps, I don't know, 3 steps from node 0, and let's inspect the results. So the first thing we're going to do is form the, unless I've screwed something up. First thing we're going to do is we're going to form the index, and we expect this to take some amount of time, however long it takes to, all right, cool. Apparently I'm bad at writing tab. Where is that? In the inspect. No, I'm sorry, not in the inspect, down here. All right, got the wrong slash there, because that's still the wrong slash, isn't it? There we go. that's just embarrassing. We can't let, even though this could take some time to recompile, we can't let that stand. Let's not bother giving this a name, and let's admit in our join computation that we don't really care about nodes. But okay, if we look at this for a moment, this is down, I'm sorry that's down at the bottom of the screen. I wonder if we can push this over to the right. It's still going to be at the bottom, isn't it? Yeah, it's not super helpful. Well, anyhow, it took 300 milliseconds to identify 100,000 neighbors of node 0. Cool. Having taken 12 seconds to load the graph and slap it into the indexed representation that join requires. Yeah, and I'm just going to rebuild it so that we can have it in the same state. Yeah, this is basically what we're looking for. I assume this is the correct answer. How could it be wrong, right? But yeah, I don't know. Maybe this could be faster. Who knows? I'm not at this point not too worried, or at least it's fairly liberating working with a slightly higher level framework than timely data flow, because absolutely there's some inefficiencies in the way, and you stop worrying about getting the bleeding edge performance and everything, and you just delight in the fact that works pretty well. And if we actually had some program now that wanted to interactively ask about neighborhood set sizes, it could get them out in hundreds of milliseconds, or more or less depending on the sizes of the neighborhoods. But we wouldn't have to reload the graph every time, or rebuild our programs all the time. These few rebuilds that we're doing now take enough time for all of us. Yeah. Well, maybe let's think about the next program. What's a good next one to do? I'm kind of inclined. Actually, I'm kind of inclined to do, if you don't mind, is to factor this out into a method so that you can more easily copy and paste this code around and just change the associated method. And actually, well, it's more complicated than that. I was going to say it would be really cool if we could, over in our lib, set up the harness. But I suspect each of these folks are going to have different types of arguments that come in and stuff like that. So let's not do that. But we can, for sure, down here, write some function that is going to do neighborhoods. And like lots of timely data flow programs, it's going to be generic with respect to a scope in which it is meant to run. And it is going to take some edges and source. The edges are going to have type collection of G, comma, edge of node barf. Yeah. And source is going to be a pair of, sorry, it's going to be a collection. G and what is it? It's a pair of node and iter. And we're going to produce, as a result, a whole bunch of pairs called collection G, pairs of node, comma, node. You might say that's an edge, but no, like semantically it's a little different. These are those nodes that were reachable in the specified number of steps. So we're going to steal approximately this stuff here. No, not nearly that much, sorry. This stuff here. Let's tab it back a little bit. So our source goes in there, edges get entered in, and yeah, maybe that just works. So we can instead write up here neighborhoods of edges and source. And then we can just trash all of this stuff down to here. And So some errors. What are? Oh yeah, sorry. We need to move all of our using statements more or less down to. That's not the only thing, is it? We need to tell everyone what a collection is. And we'll need to tell people that edges are a thing. Edge here. And I think we're going to need to pull quite a lot of these. No, I'm sorry. Using statements are all. No, they're fine. They're all globally scoped. Let's see if this looks better. No. Right. Okay. We need to add some constraints on G, because this doesn't work for any old type G. It needs to be a timely data flow scope type, where G implements. I think it's just timely data flow scope. I don't usually write this too often. And we're also going to need G. G has an associated timestamp type, and that needs to implement differential data flow lattice. This is what allows differential data flow to work its magic. There needs to be some fun properties of the timestamp type. All right. Expected U32 found tuple. This is super hard to read over here on the side. Sorry. So scope, I guess. Are there some other errors in there? Expected 32 found tuple. So expected. Oh, I see. The prep work that we've done, we should also move down as well. Right. That might have been the source of a lot of the confusion, so let's do it again. Great. All right. So this is now a little bit more reusable, maybe for other methods, where we can keep probably a lot of this. We'll have to tweak, our arguments, and we might have to tweak our additional input sources, but we probably expect roughly the structure of like load up the graph somehow, and then do some work with the sources. So let's do that actually. Let's steal all of this code. Let's steal it that way. Select all, copy, and we'll go over to reachable over here. Drop it down. I'll do reachable. Now this reachability computation is a little different. We're still actually going to get, our sources are going to be pairs of nodes, and we're going to return, let's say, pairs of nodes. So the intent here is we've got a bunch of directed edges. We have some requested pairs, source and destination, and we're supposed to return whether they're connected or not. And we can just, our collection will, output will basically be a subset of the input collection that's actually reachable. So instead of sticking a bool on them, we'll just return them or not based on their reachability. So this, something like this already exists. I'm just going to go show you it. This is over in differential data flow's graph algorithms. Stop this Dijkstra thing. Let's get this open, and this is a method that takes it's generic with respect to graph and also a node type, and it takes basically does exactly what we want, except it also tells us a distance. So we're gonna be able to do something very similar for the SSSB computation, but in principle, actually, we might not even need a little function down here. We could possibly just call into Dijkstra up here. So what would this look like? So this is differential data flow, : algorithms, graphs, maybe? Where does this live? Stop typing. This lives in graphs, in algorithms. Yeah, cool. Graphs, Dijkstra. And it takes, I think, edges and also the source. Double check. Reference to edges and a reference to the goals. All right. Maybe we should call this goals. I don't know. To be honest, this is going to be really similar. We're going to take in two integers, the source and destination. Goodness. This is now a node. I'm not sure it matters, but it's a node. And let's say that instead of sources, we're going to have these things be goals. This is just to remind ourselves what in the world's going on. Goals. Oh, sorry, it's up here, isn't it? Goals. And we just delete this nonsense. Goals. And now everywhere, to be honest, everywhere we say sources, just say goals. I hope that's true. But yeah, so source and target. And what else do we need to do? We need to, this will tell us the distance. I guess that's fine. We might need to suppress it to fulfill the requirements of the task. Bin, reachable. Okay, I got some errors. What are our errors? This is not a function. Is that okay? Because it's in. This is actually not only the name of the method, but also the name of the scope. The mod, rather. Sorry. Cannot find a target. Did we not call it target? We call it steps. Yeah, great. Some sort of error. Why did I? Okay, it's called by Dijkstra in the Dijkstra. Okay, okay. This is. I think at some point I decided that it wasn't super appropriate for Dijkstra to have a poor name mangled that way, but then I got over it. Sure, he'll be fine. Dead, right? Sweet, and maybe let's tidy up some of this crap, because we even cares. Collection, and iterate, and join, and threshold. Sweet. So, yeah, great. Cargo build, bin, what was it called? Reachable. So I actually have no idea which nodes are reachable from others. Interestingly, these computations, reachability computations, take the longest time when two nodes are not reachable, because you basically have to explore the whole graph. Right? Like, if there's any edge you haven't looked at, that in principle could be the last thing you need to connect everything reachable from your source to anything reachable, anything that can reach your target. But where things are reachable, actually this actually returns really quite quickly. It's nice. Why did I build a debug version? That's silly. Sorry about that. But yeah, this bidirectional Dijkstra method is actually pretty cool. It's a little counterintuitive sometimes because it does some things that are, in principle, wildly expensive. But because things in the computation are often so fast, it's not nearly as problematic as you might think. And the intuition, the understanding of bidirectional search is that from a source and a destination, rather than trying to go from the source to the destination just in that direction, you can simultaneously go from the source outward and from the destination backwards. And if those two ever bump into each other, you're done. Or at least if you're looking for the distance on unweighted edges. Or if you're looking just for reachability, for example, both of which are true for us. And that ends up being a lot faster, especially in graphs, because when you think, how many nodes do I need to look at? If imagine that there's a distance d between these two nodes. So if you look at the size d neighborhood around source, that's potentially a lot of nodes. If the target is random, that's like probably on average most of the graph, because got to look at a lot of the graph to find everyone you can reach. Now, on the other hand, if you go out from source d over 2 and you go back from target d over 2, that can be a lot less of the graph. And in a lot of sort of exponentially increasing neighborhood size graph models, it's more like a square root of the number of edges, which is amazing, right? If you're thinking about dealing with billions of edges and someone says, no, it's not billions that you need to look at, it's just 30,000 or something like that. This is a massive change, and things can go really quite fast. So we still need to supply this thing some arguments. I feel like we should maybe just hardwire the arguments. Source, we know 0 is a node that has outgoing edges. I don't know, maybe 1 is something we can reach? Who knows? Oh, yeah, it's going to be annoying, isn't it? It'll take us, what, like 12 seconds to learn whether, I was just going to try interactively trying out a few different node identifiers, see who could reach whom, but yeah, we have to load the graph each time we do this. That's dumb. Yep, they're reachable. I don't know, that took a little less than 20 milliseconds. They might, I mean, they could just have an edge between them. It's possible. In fact, I think we could peek at the graph and see, actually, and it probably is true that there's an edge between them. So it's not a super exciting search to have done, but at least you get the point that although we loaded the graph, it took quite a while because bidirectional Dijkstra requires both directions of edges. So maybe that's one reason that you might only want to go from source outwards, is that you only need the edges in one direction. Bidirectional Dijkstra, bidirectional search generally needs them in both directions, so it took about twice as long. But you can see here that having loaded the graph, search can be very fast. It doesn't have to be, but it can be very fast. Great. Oh, right, because we didn't, well, no, I was going to say because we didn't throw away our distances, I was thinking, no, that's too bad. I was thinking we would see the distance. What did we get back from? Oh, I see. We only kept the goal, we threw away the distance associated with it, which would have told us if it was just one hop, or maybe more hops. one could actually just write, like at this point you could just have a loop that reads from the console, so we could just type these things in interactively and see how long it takes to find them. I don't know how to do that off the top of my head, so I don't think we're gonna. But let's copy paste. Just watch how amazingly easy this is. Single source shows path. Ta-ta! And all we need to do now is not discard the distance. Ta-da! We don't really need to consolidate anything either. Why were we even consolidating anything in the first place? That's mental. Delete. Save. We don't need to consolidate anything over here. The consolidation in principle was there to, if we were over here when we were counting up, how many people are in the neighborhood, we don't want to see 1 million records. But over here, we have a single query going in, and we expect that exact result to come back. So single source shortest path also done. Yeah, pretty smart of us. Except we don't need to consolidate anymore, apparently. Ta-da! Alright, so that's done. So we're halfway done. We've done our from scratch graph neighborhood computation thing, where you can interactively ask from a source node and an interactive number of steps, how far would you like to go? And it'll tell you, at the moment at least, tell you how many people are in that set. But it will have determined the distinct reachable nodes also. Using the magic of bidirectional Dijkstra, we have computation that loads up and does some reachability testing for us, also some shortest path computations from a source node to a target destination. That might have to change. Given source and destination was specified as part of the problem, but actually it's more common that people ask for all distances from one node to all of the places. A bit like the neighborhood query, except you never stop. We could almost certainly write a version of the neighborhood computation that told us, that allowed you to specify a stopping point and told us distances to everyone within that stopping point and cool stuff like that. So we just have a few more. They're largely already done for us, so let's sort of copy paste in some stuff and talk through what's going on. I believe we have our buffer. Yeah, cool. So connected components, as we're going to do it, is an instance of label propagation, which is an algorithm that, given a graph, and we're going to need to make it an undirected graph. Get rid of this letter S also. But we're going to make it an undirected graph, and on that undirected graph, we start every node out with a label. This is typically its own identifier, the node's own name. And repeatedly, we set up an iterative computation where repeatedly we exchange these labels between nodes. You tell all of your neighbors about your label. And every round, every node says, what are the labels I've heard of? And it picks out, let's say, the smallest label that it's heard of, including its own label. And and the process repeats. And you can sort of see that within any connected component, whatever the smallest label is in that component, it will start to flood through the component. And eventually it'll stabilize as being the label that everyone in that component has. And until that's true, each round of label exchange will make a little bit more progress. So this is a perfect iterative fixed point computation. This is exactly something differential data flow is meant to be good at. So let's open up. Let's open up the label propagation code and see how to use it. Over here in differential data flow, again in algorithms, graphs, propagate. So propagation, there's two methods here for propagation, and I'll explain why. There's sort of vanilla propagation, which repeatedly, it starts from nodes and labels and a graph, and it repeatedly propagates the labels around on the graph, taking the minimum label. Now I've just chosen for it to be the minimum one. That's what's baked into the logic here. If you want a different minimum label, a different choice of labels, you specify a different L that has a different minimum, property. But yeah, if we just did this, if we just did propagate, let's do this because the second algorithm is important and interesting for a good reason. Propagate, propagate. And these are not goals anymore, they are labels. And we will need to, we actually don't have any inputs to connected components. So, screw that. But what we do need to do is find some initial labels for our nodes. And to do that, we're going to need to, this is a surprisingly expensive part of the computation, so in terms of like high performance graph connectivity stuff, we should actually think a little bit harder about this. But we're going to let labels, I'll explain why, let labels be edges dot, we'll need to also symmetrize the edges. Let's do that first because that'll make the label generation easier. Let edges be edges dot map and if we have source comma dest, we want to swing them around and do dest comma source, so the other direction of edges to which we will concatenate edges itself. So this gives us both directions of graph edges. We could do a distinct at this point, or we can also just leave it because it's not harmful. If we had edges that were already symmetric, we now got double copies of them, but it's not a big deal. All right, now our edges we can take, and anytime we have a edges dot map source comma don't care source comma dest, we can produce a labeling source comma source. So we're starting each node with its own name as a label. Let's just do a distinct here to. Again, we don't really need a distinct, and we don't really need to put all these on different lines either. We don't really need a distinct because the label propagation algorithm will take care of that for us. But might as well. And this is the surprisingly expensive part of the computation because although we do some graph propagation stuff elsewhere, we actually shuffle around data proportional to the number of edges, which is silly, but we do it anyhow. And yeah, you get surprising benefits by doing, for example, mapping this just to source, not to pairs of source, calling distinct only on the source, and then mapping it out into pairs afterwards because you've reduced the amount of data distinct needs to work with by a factor of 2. Stuff like that we're just going to ignore for the moment. We'll maybe do another video later on where we try to do a little bit of performance engineering on these things to make them go a bit faster, to get the sorts of numbers that we see when we do benchmarking for papers and stuff like that. But we've got some labels. We've propagated our labels. Does this build? This might build. Oh no, it won't build because we have got like weird stuff that we don't actually need. We don't even have a thing called goals. So it should just go away. And we don't really do anything here. So what this looks like instead, when we don't have any input, we essentially write the following. So the worker.step method reports back and says, do I have anything else left to do? And so we just run it until it says, guess I'm done. And that's the only number we really need to see. All right, got some errors here. We don't have a distinct thing in. That's totally true. What else don't we have? VO, I'm sure that's a typo. Typo, just like a stray bit of crud. That's all maybe? Let's see. Go around again. Cannot find handle, that's great. We don't actually need handle, so Yeah, cool. So cool. We don't need graph node and we don't need input either, so I suppose we tidy those up while we're here. And we're going to run this, and it's going to take a while to run, probably. We're going to learn about the difference between propagate and propagated at. So like while it's running, let's say, while this is building, let's do while it's building because that'll take a minute at least. So what's the difference between, okay, propagate circulates these labels around and keeps them in a label. That seems pretty smart. Why don't we do that? So if we do that, what happens is that we've got maybe some large connected components in our graph. They've got a lot of labels in them. Every different node has its own label. And our iterative computation is going to start circulating these labels, which we expect. And a lot of nodes that are not, who have not yet received the minimum label, are going to have a lot of arguments about which crappy label that is not the minimum label they should work with first. So while label, let's say 0, is starting to move through the graph, everyone else is saying, like, I'm label 5 million, pay attention to me. And someone's like, no, I'm 4 million. And they basically bicker for a while. And that's all data that we have to keep track of and deal with, and because we're faithfully representing that computation. Let's see if we can. And we want to inspect it. What were we inspecting? Hold on, sorry, my mistake. No, we don't want to inspect this. This is all of the labels going on. So let's just, this is fine. Let's just say false here instead, rather than recompile them. Sweet. So this will run, and while it's running, let me get up the activity monitor just so that we can know if things have gone horribly wrong. So what propagate allows us to do is to bring a little bit of logic into play that says, for each of these labels, when should we start circulating them? Should we start all of them at the beginning, or should we possibly delay some of them using a function that says, for a label, give me a number, and I will delay them based on that number. And what it does, it has a rule in mind where it says, informally, think of this as a hash. Right? So tell me something that gives me a hash, and I'll circulate whoever has value 0 first. If it's a hash, maybe no one gets that, but bear with me. And having done that, I'll circulate 1 and 2. And having done that, I'll do 3, 4, 5, 6, and so on. Maybe I might have this logic a bit wrong, but basically it's looking at the number of leading zeros in that number and giving the computations, giving the earlier labels a bit of a head start based on the number of leading zeros. And this allows us to take our labels, which actually we happen to know are 0 up through nodes, and say, why don't you give label 0 a, in this case, 256 round head start. That's pretty good. That means that it's probably going to do a pretty good job taking over its bit of the graph. And from that point on, later on we introduce 1 and 2, and 1 and 2 both show up and say, I guess we're done here. If they're in that large connecting component, I guess we're done here because nothing to improve on. There's already a 0 here. Great. So instead of bickering about who gets to be 1, who is a 1 person and who's a 2 person and all the other labels out there, mostly we just circulate zeros and then confirm that we got the correct answer. When other labels show up, we double check our notes and say, like, yeah, cool, you've already got a label 0, I guess we're done. If by chance node 0 wasn't connected, node 1 would say, like, oh, my turn, awesome, and it would race through the graph. And the geometric sizing here, this sort of leading zeros thing, is meant so that in a connected component, if it has a random set of these labels, then whatever the smallest label happens to be, it doesn't have a large number of peers that circulate with it at the same time. How are we doing on memory? Quite a lot of memory being taken. But less now. What happened? Wow. Well, in principle, we can let this run. I can also, what we're going to do is supply a function logic that says use the label as the U64, and that's going to make things go a fair bit faster. I'm sort of curious, hopeful that we can actually get a report out of here, though, so that you can then see how much faster it goes. The risk we face is that we are, in fact, writing down all of that crud about the different labels, and when the labels are fighting, just using propagate, not propagate at, when those labels are fighting, we make notes about all these things because that's what the computation said we had to do. And yeah, we might just exhaust some memory. We probably shouldn't, to be honest, because differential is pretty clever, and as we go by iteration, it'll be compacting the histories, and iteration by iteration. Like once we reach iteration 5, 6, 7, whatever, we don't really care about 5 or 6, and those data will be folded in, and the distinctions between them won't be retained. Though we're probably exercising the allocator quite a lot here. But I'll prep and not save what we want to write. Cool. So that's the only change we need to make to the code. I mean, we'll need to save the file, and then we might need to do a cargo check and fix some reference versus not reference issues. I don't want to do that though at the moment. I want to let this run for a little bit. But this is I think a great example for me, at least a great example where something like differential and timely data flow allow you to do a thing that's a little harder to do in other programming environments. So for example, you can write this propagate logic up here in a modern data log fragment where you say, yeah, start circulating these facts for me, but only retain minimal facts, something like that. But you don't really have the ability, the way we did down here, to schedule the movement of those facts. And that doesn't change the answer. These both arrive at the same conclusion. But it massively changes the performance. All right, so that took 350 seconds. And I'm hoping that we don't have to take that much time again. Let's cargo check this. Looks great. We do have to rebuild, but it's too bad. So this is an example where scheduling computation. This is something that when we write imperative programs is super easy, right? Like we're in control of what the computer does at any particular point in time, so we can choose do this before doing that. And in more declarative languages, things like Datalog or SQL or what have you, you have much less direct control over when a thing happens, because you're not, the degree of freedom that you're giving up in these declarative languages is that precise control. The system says, don't worry, I'm really smart, I'll figure this out. And yet, unfortunately, most systems aren't bright enough to figure out things like if you have a minimization aggregation, circulate these minimal values first. They might, we'll see that probably in Sigmod 2025 or something like that. But for the moment, at least, it's super helpful to be able to put in a little bit of imperative flavor saying, introduce these data in some particular round of computation. Ideally, this will take fewer than 350 seconds. sure if it'll necessarily take much less memory, but and one of the reasons we like things going a little faster here is that this is, variously part of the secret sauce that lets laptops go as fast as cluster computers, right? Is using smarter algorithms than the cluster computers, because the cluster computers chose frameworks that gave up expressive power in the interest of scalability, and unfortunately have to use that scalability. There we go, we're done. Have to use that scalability to recoup the cost of doing these things. So this is 5 times faster, basically. So if you're thinking, how many computers should I need to rent to do graph connectivity, and you're thinking I'll use some fancy data log thing, not even Spark or something like that, but like data log on some Apache infrastructure, versus differential data flow, which allows you to schedule these things, you can, in principle, use 5 times fewer resources to get the answer. And I think that's valuable. But okay, that's that. That's graph connectivity. We're done there. Again, these things could, in principle, be optimized a bit. A surprisingly large amount of the time is actually up here, screwing around with finding the initial labels. And if someone had told us what is the initial set of labels, like what are the nodes in the graph, this would be a lot faster. I think when I've done this in the past, it's like twice as fast, essentially. In part because the propagation is now, there's really not a lot of work going on there. Now that we're just doing this small label propagation, we sort of visit each node in the graph once, and then confirm that all of the other labels aren't that interesting to us, and we're done. All right, triangles. Triangles is something that we have. Let me steal some code here. Triangles does not involve an input, so we can just steal this code. And we've already got a few versions of this written. If you've been watching these videos, the last 2 videos involved triangle computation. And we can just wander on over to projects. My icon went away. Where's that? Differential data flow, docs, examples, and go to go et al, which has a method that determines triangles. And this is a special triangle computation method. It is a worst case optimal join triangle computation method, which means that it takes a lot less time than stupid algorithms. Sorry, that's not fair. Stupid, not stupid, but like if you just did a few relational joins using binary joins, you have the potential to take a lot of time doing your computation, because it's bad. Again, bad algorithms, or at least inefficient algorithms that trade away efficiency for a simplicity of expression, something like that. All right, we're gonna need to bring edges and nodes back to life. And rather than all this stuff, we're just going to do we don't need any labels, and we certainly don't need weird arguments to the triangles method. And there was some confusion. I didn't understand whether we were supposed to be doing directed triangle motifs in directed graphs, or triangle motifs in undirected graphs. Let's just, that question needs to be resolved. So we should, if we're looking for undirected triangles, we should take all of the edges and orient them from small to large, and then distinct the results. And if we're looking for directed triangle motifs in directed graphs, so we can just run the code as it is, and it will find instances of triples A, B, C, where A points to B, B points to C, and A points to C. Now, I didn't change all of this text in each of these things. This could be going to be really annoying, isn't it? We can just count up the triangles. We don't need to see any of these, do we? Let's actually, well, let's make it undirected because I know the correct answer for this graph in that case. So all we're doing here is just putting them in the small to large direction. So if the source is less than the dest, great, leave it that way. Otherwise, flip them around. And I suppose distinct at the end. This is one of these things that, like, yeah, maybe we need to do this, maybe we don't need to do this. Sometimes the input data are assumed to have these properties already. The graph benchmarking space is a bit of a mess because there's not a lot of consistency on who reports which times from their computations, and some of these things take surprisingly more time than you think. Spell triangles right. Does this just build, maybe? Oops, yes, that's not how you do it. What's that? Can't find collection, captain. What have I screwed up here? Unresolved import graph, but hold on, didn't we, oh no. No, I made this again, sorry. Graphs, cool. I need to correct some of this lingo down here. And I don't know how much of this is strictly necessary, but we can instead so those are some of the constraints that we assert that we needed back when we wrote this the first time. We need some new types here. We need to not have that anymore. We're going to need collection. It just as collection? What? No, that's a terrible idea. Why would you? As collection. Yeah, that's we don't want that idea at all. It's terrible. Range by self. Amazing. Or that range by key. We also need that apparently. Join core, cool. This experience is basically maybe concluded 100% of all methods will be inherent on collections. Screw you and your modularity. I don't care anymore. Reduce, for fuck's sake. This is... I mean, I think the real problem here at some level, not the real problem, there's a bunch of problems, but Rust has difficulty moving past each of these undefined things because it has no idea what the next issue is going to be, and the reduce is on the output of the join. So if we had given them types along the way, first of all, we would have been here forever, but we would have at least seen the spray of errors concurrently. All right. So this triangles method looks pretty hilarious. I mean, it's really big and complicated, but it's actually not such a bad idea what's going on here. It's a fairly standard algorithm, actually, where we take each edge, edge AB, and say we're really interested in those values C, where A points to B, and where A points to C and B points to C. But the way we should find them is by first asking which of A and B have a larger out degree. Now, why do we ask that? That's because it is easier to take the node with the smaller out degree, let's say it's B, and have it propose a bunch of candidate C's and then intersect them against A's candidates, essentially, than it is to have A propose all of them and intersect them against B's smaller set. When we do it the first way with the smaller, like B or whomever it is, we do work proportional to the size of the smaller number of proposals, and a little bit, like logarithmic with respect to the larger size. But that's great. That changes the asymptotics of the computation substantially, and it makes the computation robust against issues like, I'm not sure what the maximum degree is in a live journal data set, but like I've got other data sets here where the max degree is 45 million. And if for each of the 45 million edges coming out of that node, we proposed 45 million other nodes as possible triangles, we'd be here forever. It's just a massive amount of bad use of time. And this algorithm essentially hardens the computation against that. It says, no, for each of those 45 million proposals, someone else should probably do the proposing for C. Right? It's too bad that we got 45 million things we have to deal with, but we'll let some other node be the one to propose the extensions. We just need to verify them afterwards. And that's good. It takes things from utterly unreasonable to only slightly unreasonable. And to be honest, I have no idea how long this is going to take, actually. I apologize. I know how long it takes in like a fast, timely data flow implementation. This is not a fast, timely data flow implementation. This is just a timely data flow implementation. And what did we decide about inspect? That was just counting them. Great. So let's inspect it. Cool. This is a thing that takes single-threaded, 12 seconds if you've done everything right. So if you're running hand-rolled code, it's about 10 lines of code. It's not even very much. Hand-rolled code, it takes about 12 seconds on my laptop. And there's timely data flow versions that also take about 12 seconds that are largely just having each worker do the same thing that a single thread would do, just on a fragment of the graph. This is going to do quite a lot more. And no idea. There are better versions of this algorithm. So in the docs repo, there are other implementations that use smarter update rules and store less state and are generally pretty slick. But I'd have to take in a dependence on a non-crates.io crate, which, in principle is fine, but this is maybe a little bit better if you want to share it with other people. It's definitely slower. Just realized that some of these things we could make even faster if we wanted to by changing this from a 0 to the empty tuple, because the empty tuple is what lets us say our timestamp is nothing. And right now, whatever this is, probably an I32, just by default, is getting packed onto all of our diffs and is taking up an additional 4 bytes of space next to all of our I-sized diffs. So actually it's probably another 8 bytes basically on every single record we're dealing with. So we could thin that down almost by a factor of 2, I guess, which we just manage a lot less data as we shuffle things around, and probably each of our algorithms go some small fraction faster. But this fact that this is a 0 instead of an empty tuple is buying us nothing in this computation. There's just a whole lot of 0 values flopping around where we would have written a timestamp, and we should just write nothing there instead. Let's see how this is doing space-wise. Okay, it's taking some space. Might take a lot of space. Don't really know. I suppose while that's running, since I have no idea how long this could take to run, let's start talking about PageRank. PageRank is another one of these things that already has an implementation, which is lucky. And I happen to know that the implementation isn't especially brilliant. It's interesting, but it's not especially brilliant. It was compared to in a paper at Eurosys called GraphBolt. And GraphBolt did incremental updates to graph computations, including PageRank-like computations, and also including reachability-like computations. And they compared against differential dataflow, and they went faster than differential dataflow for PageRank, but differential dataflow went faster than they did for reachability queries. So it was great. Everyone got to win at something. Here is PageRank. What does it take as input? It takes as input a bunch of edges where I've specified the diff field. Wow. So this is pretty trying to be pretty clever, I think. We could just ignore this for the moment and just let it be an I size. 64 bits is probably enough. And what the algorithm does, let's give you some space here. It's, not too long. Some of this is if you're allowed to optionally specify a number of iterations that you should run and then terminate, or if you use 0, then you just run to convergence. So some of the extra lines there because of that. But no, like what it does, it's a differential dataflow is pretty bad at continuous math. And PageRank typically involves continuous math in its formulation. There's some continuous fraction of probability mass at various nodes in your graph. And iteratively you circulate that probability mass around. Floating point numbers get smaller and smaller, not smaller and smaller, but the changes get smaller and smaller. And eventually you stop. And since they're real numbers, okay, no, you shouldn't ever stop. You should just go forever. So people, I think it has to do 20 iterations because 20 is the magic number that people use. This code can do any number of iterations, and it does some smart things about incrementalizing the computation. But the way it does this is it takes a slightly different approach. It says instead of using floating point numbers, we're going to use fixed point numbers. Which you might say, sorry, what does that mean? And the idea is that we're going to take, let's say, 64-bit numbers, and we're going to, instead of trying to represent the number 1 as 1, we're going to represent the number 1 as something like, I think it's going to be about 6 million. We'll see. There's, oh dear. I think we used too much memory. Yeah, okay, let's kill that just for the moment. Like the Command Q is right next to Command J, which minimizes things. So let's get VS Code back. Maybe we'll return to triangles, maybe not. This problem is absolutely solved by using the dogs implementation. But where are we in PageRank? Rather than having the value 1.0 associated with each node, we're going to use a big integer. We're going to start with 6 million things at each node and start circulating them fractionally around, where we have to move integral numbers of these things because we only work with integral counts of things. But by having 6 million units, these are surfers. The original intuition behind PageRank was you had random web surfers on the web randomly clicking on links, and that was the motivation for the process that distributes real valued rank around, was the fraction of surfers that you had. No, we're just going to use integral surfers there, and enough of them that we get a decent approximation to the real number that we're trying to track. And we could use, if we're using 64-bit numbers here, we could use something really quite big actually if we wanted. This uses only a certain amount of precision below the decimal point, but that's actually fine because the way PageRank works, you fold in this fractional amount each time you go around, so you don't get to see low detail. You don't get to see high detail in the low bits anyhow, because you're every round clobbering the low bits with a bunch of reset probability. So okay, more concretely, what does this look like? We get our nodes out of our edges. Great. We also compute for each node its degree. That's going to be an important part of distributing the probability mass around the surfers. Then we start up an iterative computation here, where I've allowed us apparently to set iter and to set diff because I'm very forward thinking. Iterative computation, we bring in our edges and our nodes and our degrees, and we start up by saying, for each of our nodes, let's turn that into explode as an exciting method. You can tell by the name. It allows you to take any record and produce a pair of record and count. So this allows us to say, for each individual node, make 6 million of them, without actually ever doing 6 million of anything. So we'll have some initial scores there, 6 million, and some reset that's there. And then because PageRank's a little wonky, we define our own iterative computation. So you might have noticed we're not using iterate, we're using iterative. This defines an iterative scope in which we can create variables. We're going to do that right here. We can create variables. They've got some arguments. I'm not going to tell you what these mean. These are basically what do you do to the timestamps each time around the loop. But we'll start from our initial computation, our initial distribution of ranks, and then we're going to write some logic which tells us how do we move these ranks around every time. So we're going to semi-join the degrees in the ranks, and what this does is, in effect, gives us a pair of the node, its degree, and the number of surfers currently there. The surfers currently there is in the count, like it's in the multiplicity. So we use this threshold function, which allows us to look at the current accumulation of the count. I mean, we use it. The threshold is a more general method, but we're using it in this context to say, if you show me the node and its degree and the current number of surfers present there, I'll tell you the new rank that it should have, which is 5/6 of the rank divided by the degree. So each of the outgoing nodes is going to get this score. So we have to divide down by the degree to make sure that across all of the outgoing edges we don't actually inflate the rank. And the division by 5/6 is there so that we dial down a little bit of the ranks that we're circulating, and we can mix back in a little bit of reset distribution so that no one becomes permanently impoverished. And with that new weight chosen, we're just going to discard the degree and call this thing to push. This is the weight that's going to move along the edges, so we join the edges with to push. We say we don't really care where you got that weight from. Everything pushed along an edge is received by the destination. Get the destination, we concatenate in the reset probability, and we consolidate. And if someone has told us that we should use some number of iterations, we do a little bit of logic that says, if you have exceeded we use a filter that says you can stick around as long as your time is less than the number of iterations. Otherwise, off you go, you're dead to us. And then we bind our variable. So we're setting up a recursive computation. We bind our variable down here to this pushed results, and then return it. And we're good. That's PageRank. It's not the best way to write PageRank. I'm not gonna tell you you should write PageRank this way. You should probably use Timely Dataflow's PageRank project. But we're gonna try this anyhow. So we're gonna drop this in here, and we should take, I suppose, all of this stuff up here. And I suppose we could introduce the diffs and the iter type, because now we need to let's just put those in and see what happens. Five errors. Let's see. Variable. That's true. We need to remember where variable is. I'm pretty sure it lives wherever iterate lives. If you've been noticing weird typing going on, this keyboard is awesome. And it has this weird ability that if you hold certain keys down, you can turn them into modifier keys like Control and Shift and stuff like that, which is really fun. But sometimes, oh, look at that. Sometimes, for example, when you type operator, what you get is you hold down O, you type P. No, I must have done something totally different. P and then R, which is pi and then the trademark sign. But I'm not sure actually which characters I was holding down to do that. But in any case, if you type a little too fast or you have slightly chorded typing, it can screw things up. Product. So product is a timely data flow thing. We'll need to grab that out of timely order product. Triangles? Yeah, no one wants to use triangles. That's ridiculous. What do we need when we call PageRank? We need some number of iterations and then a collection. And 20 is the indicated number. This is this is differential. All right, that might be closer. Whoops. Okay. Did not catch that one. I need join so that we can use semi-join. I didn't realize we didn't have join in here. So I guess not. And count. Oh, filter. So this is like a raw timely data flow filter because we need to look at the timestamp field, which is something that differential conceals from us because it doesn't want us screwing around with stuff like that. Yeah. There are other ways to write that. We could also write a little bit of code that causes. I'm just going to tidy these things up because I want to see answers. Join core and reduce. Great. Off we go. You can set up timely data flow iterative computations to bail out after fixed numbers of rounds, but I don't think differential data flow natively does that. It allows you to do that. So we're going to run this with LiveJournal, and it should be fine. There's not, the state is linear in the number of nodes, so that's, I mean, it'll be linear in the number of edges, but the state as we iterate is linear in the number of nodes. Shouldn't blow our memory. It won't go fast, but this is something, I forget how long it takes, like a second or two if you're doing a single thread. There's just not a lot of math to do. Almost all of the time is spent poking around in main memory, as opposed to actually adding floating point numbers together is super easy. Yeah, so we're getting quite close, actually. We're just about done. In principle, I could try to fix triangles. That's a good question, what I should do with that. I could leave it as an example of like vanilla, sorry, beg pardon, vanilla differential data flow at the moment. No, it's a little tricky, actually, to write triangle computation that doesn't keep in memory a fairly large amount of state, which is, is too bad. It's nice that there's a project that addresses this, but right. That a hyphen is me trying to do a shift to get an underscore. I'm sure you're very interested in that. False. Let's see how it goes. Let's see if the memory is borked here. What do we, PageRank? Yeah, no, it's fine. I imagine it's just being slow. One of the disadvantages that differential data flow has relative to other systems in something like PageRank is that a lot of the PageRank executing systems out there are clever enough to realize that with node identifiers that go from 0 up to something small, you should probably have an array. That's a great way to represent your ranks. And differential data flow is not as opinionated as that. It's more than happy for you to run PageRank where your graph is defined by nodes that are strings. You can totally do that. And it will maintain all of your ranks in various sorted lists that it maintains fairly cleverly, but not nearly as cleverly as just take an integer, go to that location in memory, and do plus equals. So it's definitely doing a lot more work than an optimized PageRank implementation, such as the timely data flow PageRank implementation, which goes pretty fast. And amazingly, at Sigmod, some folks who weren't me turned it on and ran it on 1,000 cores. All right, 190 seconds, just to give you a sense for what that number might want to be. We can go to, if we go to CD projects cost, I forget how to, all right, we need to say something like vertex dot slash live journal. We've got live journal. And we need to tell it some nodes, which I think 5 million is enough. So each iteration here is taking, I guess I lied when I said it would just take a second or so. Each iteration is taking some fraction of a second, and the whole thing happens in 10 total seconds. And so we are 20 times slower, looks like, which doesn't bother me tremendously. I mean, it's if what you want to do in life is PageRank, you should do it a different way, probably. Again, this tells us something about what differential data flow is good at versus what it can plausibly express. So it can plausibly express PageRank, that's fine. Not necessarily good at it. Though it can do some cool things, like you could actually have this incrementally update if you wanted, which is interesting. It's something that a lot of other PageRanking systems, if they support it, only support it through the wonders of linear algebra, which says that PageRank doesn't really care where it starts from, so just make some changes to your data and keep running it. And it's something that would be a total mess in any other domain. But anyhow, yeah, we've got these implementations in place. I'm going to git commit these. And where are we? Dot slash. Is that right? Let's go back and see something a bit more credible from. Okay, before we git commit anything, cp like LDC dot git ignore into graphs. Cool. Git commit initial check in. Great. So we've got initial implementations of all these algorithms in differential data flow. Not the most performant ones necessarily. Some of them shouldn't be too bad, or some of them probably aren't going to get any better. I don't think I'm planning on improving PageRank at all. But triangle computation, maybe that could be better. Connected components could probably be better. Let's just tidy these up here so we can actually tidy up. No, but I'm going to clean up the windows so we can actually look and see what's in front of us. So PageRank's probably not getting it faster. Triangles could absolutely be faster if we use the dogs stuff. The connected component stuff, like I said, a surprising amount of time is spent determining initial labels, which is sort of silly. These two folks use bidirectional Dijkstra. That's not getting any faster. I mean, we could handle that in timely data flow in principle, but that would start to be several hundred lines of code at least, and probably lots of bugs. I don't want to do that. And I like the neighborhood stuff, to be honest. This is sort of cool. Like, you get to specify how far out you want to go in the data as opposed to in the program. So you could interactively ask, tell me about, here's a node I'm interested in, show me the degree 1 neighborhood, now the degree 2 neighborhood, now the degree 3, and sort of grow it out as you feel comfortable interactively, which is cool. You don't have to change the program at all. But yeah, I think we'll stop there for now. Hopefully this has been helpful. We've seen from scratch several different graph algorithms. I mean, admittedly, several of these I literally just copied and pasted in an existing thing. This should be fun though. Like, these things exist that we can go look at and sort of skim how they work. And ideally, we shouldn't have to write all these things from scratch every time we want to write a program. Label propagation is a pretty common thing to do. Bidirectional text shows a less common thing to do, but you don't want to write that more than once anyhow, so we feel really clever for having written it 0 times instead of 2 times. But yeah, I hope this has been helpful.